We recently transitioned into lateral load testing on the DarkAero 1 vertical stabilizer and empennage. One of the most severe loading conditions that could occur on the vertical stabilizer is if the pilot introduces full rudder deflection into the oncoming wind while already in a side slip. This specific condition was actually ill-defined up until about the early 2000s. I think there's a couple interesting points to talk through, so let's get into it. Generally speaking, the vertical stabilizer on an aircraft provides directional stability. So that's pivoting about this axis of the aircraft. There is a rudder on the vertical stabilizer which gives the pilot control authority to command different yaw angles or side slip, say in a crosswind landing. So for this test, we determined a peak load that we wanted to bring the vertical stabilizer and empennage to on the ground prior to flying the aircraft, such that we are bounding flight loads but also not overloading the aircraft and potentially unnecessarily damaging the structure on the ground. And then that's what dictated the design of the test setup or test rig itself. The test is actually set up behind me right now, so let's take a look at it. We'll start at the front and then work our way back towards the vertical stabilizer itself. Right now we have an engine mass simulator installed on the firewall. So this is just using the actual engine mount itself, but then replicating the mass or weight of the engine with concrete in case things get out of hand. We don't want to damage the engine, so we're just using concrete. This was the same engine mass simulator that we used for landing gear drop testing. On top of it we have sandbags, and then on top of the fuselage itself we have more sandbags. These are acting as a counterbalance, so when we push downwards on the vertical stabilizer, the whole plane doesn't pick up, kind of like a teeter-totter. Moving back, you can see where the foam support that's actually holding aircraft up, all the vertical reaction load would be going through this foam. That foam support stops here. Anything behind that is counteracting the bending moment or feeling the bending moment stresses from applying load to the vertical stabilizer. And so the foam we strategically placed and determined to stop it at this location to test as much of the empennage as possible while making sure we don't unintentionally damage the forward portion of the fuselage. So we can move back even further here. The gantry we just set up so that we can have something to push against. Up here, this is a hydraulic cylinder, and so as we pump or increase the pressure in that hydraulic line, the cylinder pushes downwards onto the vertical stabilizer. We have just digital levels here to make sure that we're pushing straight down and we don't have the cylinder kick out on us. So that force from the hydraulic cylinder is going straight into a S-type load cell. And so that load cell, we have a readout, and that's ultimately what we're using to determine have we gone far enough or to our target load. We're just watching that as we increase the hydraulic pressure in the system. And so that load cell then contacts this 80-20 wiffle tree. That's just a term for dispersing load from one initial application point out to multiple points or a larger area of your system. So we don't have to have multiple hydraulic cylinders pressing here, here, and here. We can just have one, and then the wiffle tree, based off of the length or arm ratio within this 80-20 frame itself, it disperses the load to the predetermined values that we want so that we're replicating aerodynamic loads on the vertical stabilizer. So that is a summary, high-level summary of the vertical stabilizer proof load test setup. Let's get into testing. This test campaign comprised of 2 test cases. So we started with the fuselage resting on the co-pilot side and loaded up the vertical stabilizer and empennage. And once we reached peak loading condition and verified that the structure passed the test, We rotated the fuselage so it was resting on the pilot side, and then loaded the vertical stabilizer and empennage to the same peak load but in the opposite direction. It should be noted that the deflection seen in the test videos is not solely due to the empennage and vertical stabilizer deflecting under load. It's actually from the test setup as a whole. So the fuselage was ultimately being supported by foam that was machined to the outer contour of the aircraft, and as that foam deflected or compressed under load, the entire aircraft and respective test setup would shift and move. This test campaign was fairly uneventful. That's actually a good thing for structural proof load testing, because we're trying to prove and validate that the structure is ready for flight without taking it all the way to failure. The one thing that hasn't been discussed is how we determine the aerodynamic loads that the vertical stabilizer structure should be designed to, as well as the respective proof load value we should use to validate the structure prior to flight testing. Determining these loads involves looking at the edge cases or worst case loading conditions that the vertical stabilizer would experience in flight. This is where things get interesting, and this topic probably deserves a standalone video, but for today's video we're going to try and provide the short version. What this ultimately boils down to is the definition of maneuvering speed. There's regulations that govern or guide pilots on how to operate aircraft, and then there's separate regulations that determine how aircraft manufacturers design, build, and test aircraft to a certified standard. So what the pilot is trained to do versus what the aircraft manufacturer is designing the aircraft for. Both of these regulations contain definitions for maneuvering speed. Typically, these regulations agree with each other, and manufacturers have designed aircraft to handle what pilots are trained to do. There have been times, however, where the regulations do not agree on something like the definition of maneuvering speed, and this actually resulted in an airliner crash in the early 2000s. In the early 2000s, the Pilot's Handbook of Aeronautical Knowledge defined maneuvering speed as the maximum speed under which maximum control deflection could be used without overstressing the airframe. At the same time, manufacturer regulations defined maneuvering speed as the maximum speed under which the controls could be commanded to maximum deflection in one axis at one time, and for most of the loading conditions, this was occurring from a starting point of steady state flight. The phrasing of these definitions may seem subtle, but this actually led to an airliner crash involving the control of the aircraft's rudder. In this case, the pilot was maneuvering through wake turbulence under maneuvering speed with the understanding that controls could be commanded to their maximum deflection regardless of their previous position. This resulted in a rapid control reversal of the rudder while already in side slip. Doing so imparted more load on the vertical stabilizer than the aircraft manufacturer designed the aircraft structure for, and resulted in the vertical stabilizer structurally failing and departing the rest of the aircraft. The safety board investigating the crash ultimately concluded that the accident stemmed from the discrepancy in maneuvering speed definition. Since then, the regulations have essentially flipped. So Part 25, which is the regulations manufacturers use for certifying transport category aircraft, now talks about control reversals and rudder doublets. And then the Pilot's Handbook of Aeronautical Knowledge more tightly defines maneuvering speed as being able to command the control surfaces to max deflection in one axis at one time. We took all of this into account, among other things, while designing the DarkAero 1 vertical stabilizer and determining what proof load to validate the structure with. Validation of the vertical stabilizer and empennage structures is another completed milestone on the path to ultimately reach production of DarkAero 1 kits, which is something we've been documenting progress on our website. If you're interested in owning design and development of aircraft structures or systems, performing tests like what was shown in this video, or even building aircraft, you should apply to join our team today. We're hiring engineers and technicians to not only help accelerate efforts on the DarkAero 1, but other aircraft with unique capabilities as well. Check out our website and apply today. With work wrapped up for validating the vertical stabilizer and empennage structures for flight, we're moving on to load testing the engine mount. We'll save that for another video though. Thanks for watching. We'll catch you next time. Fun fact, it's actually negative 18 degrees Fahrenheit here in Madison, Wisconsin. So the density altitude of the local airport here is negative 5,000 feet. On a more standard day, it would be around 1,000 feet. I mean, I think that's cool.